12 seconds. That is how close Apollo 11 came to running completely out of fuel while still hovering above the moon, with no way to abort and no way to know whether the ground below was even safe to touch down on. It was the 20th of July, 1969, and inside the spidery lunar module Eagle, Neil Armstrong and Buzz Aldrin were living through the most dangerous 7 minutes of their lives. Alarms were blaring inside the cabin. The onboard guidance computer, responsible for calculating their descent, was overloading and spitting out error codes neither astronaut had ever seen during training. Down on Earth, a 26-year-old engineer named Steve Bales had mere seconds to decide whether those alarms meant the mission had to be aborted or whether it was safe to keep going. Get it wrong, and 2 men could die live on television in front of hundreds of millions watching around the world. This is the story of what actually happened once Apollo 11 reached the moon, the near disaster almost nobody knew about for years, and the discovery scientists are still struggling to fully explain more than half a century afterward. To understand just how close this mission came to catastrophe, go back to the final minutes of the descent. Armstrong and Aldrin had already separated from Michael Collins, who remained alone in the command module orbiting the moon, and begun their powered descent. Roughly 6 minutes in, a warning tone filled the cabin, followed by a cryptic error code, 1202. Neither astronaut knew what it meant. The guidance computer, a machine with less processing power than a modern pocket calculator, was being asked to handle more data than it was designed for, because a rendezvous radar switch had accidentally been left in the wrong position, flooding the system with unnecessary information. Back in Houston, the alarm lit up every console at once. If Mission Control had ordered an abort at that moment, Apollo 11 would have become a historical footnote instead of a triumph. Flight Director Gene Kranz turned to Bales, whose job was to monitor exactly this kind of guidance failure, needing an answer immediately. Bales made the call to continue, trusting the alarms meant the computer was simply overloaded, not broken, and that it would keep prioritizing the most critical landing calculations while shedding lower priority tasks. It was an extraordinary gamble made under unbearable time pressure, and it turned out correct, but the alarms kept returning throughout the descent, each forcing the same nerve-wracking decision in seconds. As if a malfunctioning computer were not enough, Armstrong then discovered a second, far more visible problem. Looking out the window, he realized the guidance system was steering them toward a boulder-strewn crater roughly the size of a football field, littered with rocks large enough to tip the spacecraft over. There was no time to consult Mission Control. Armstrong took semi-manual control, flying the module like an aircraft, searching for anywhere flat enough to set down safely. This decision burned through something Apollo 11 had very little of: fuel. Every extra second hunting for a landing site was fuel that could never be recovered. In Houston, engineers watched a single number ticking downward, the remaining seconds of burn time before the tanks ran dry. At 60 seconds remaining, capsule communicator Charlie Duke gave the crew a call-out warning that time was critically short. 30 seconds after that came another call-out, and the room went almost silent, because 30 seconds of fuel leaves no room for a second attempt. It leaves room only for landing or crashing. Armstrong finally spotted a relatively flat patch beyond the boulder field and eased the module down, kicking up a cloud of fine gray dust that obscured his view in the final moments before touchdown. The Eagle settled onto the sea of tranquility with somewhere between 15 and 25 seconds of fuel remaining, so little that engineers later admitted the mission came within a hair's breadth of either a fuel-starved crash or an emergency abort at the worst possible moment. Armstrong's now famous words confirming the landing were delivered in a voice that betrayed just how tense those final moments had truly been. With the spacecraft finally down, the immediate crisis was over, but a new set of dangers was only just beginning. Leaving the lunar module meant exposing themselves to one of the most hostile environments imaginable: brutal temperature extremes, dangerously low pressure, unfiltered ultraviolet radiation, and fast-moving micrometeorites. Simply wearing clothing was never going to cut it. What NASA engineers built instead was closer to a wearable spacecraft. Its first job was to stop the astronauts from effectively boiling alive within seconds. Because in near total vacuum, without atmospheric pressure pushing back, water boils at normal body temperature, including the water inside human blood. 3 components worked together to prevent that. First came the pressure bladder, an airtight rubbery inner layer holding in a pure oxygen atmosphere, essentially a human-shaped balloon. A balloon under pressure naturally wants to expand, though, so a tough, high-strength woven fabric wrapped tightly around it to hold the suit's shape steady, letting the astronauts actually bend their arms and legs. Finally, strapped to their backs, was the portable life support system, an iconic backpack supplying breathing oxygen and maintaining internal suit pressure at roughly a quarter of what we experience at sea level on Earth. Not much, but enough to keep them alive. Pressure was only half the battle. The suit also had to survive temperature swings plunging below minus 100 degrees Celsius in shadow, while soaring past 100 in direct sunlight. Engineers built it from more than 20 layers using a dozen synthetic materials, most packed into the outermost thermal and micrometeoroid garment, combining reflective materials to insulate the suit and bounce solar heat away. Wrapped around the outside was a tough, Teflon-coated glass fiber fabric, giving the suit its bright white appearance, shielding astronauts from radiation and abrasive lunar dust. Strangely, the astronauts also needed protection from their own body heat, since working on the surface was roughly equivalent to a strenuous workout, yet there was no way to remove a layer to cool down. Engineers built a network of thin tubing into an undergarment worn against the skin, constantly circulating cool water to carry excess body heat away. Heat was not the only invisible danger. Without an atmosphere to filter it, the astronauts faced a nonstop barrage of ultraviolet and infrared light, leading to one of the most recognizable features of the mission, the gold-coated visor covering their helmets. An extraordinarily thin layer of real gold was applied to a polycarbonate faceplate, turning it into a highly effective mirror. Gold does not oxidize over time. It can be worked into an unbroken coating across an entire visor, while cutting down blinding solar glare enough for the astronauts to make out their surroundings. Because gold filters infrared and ultraviolet so effectively, the lunar surface likely appeared slightly more blue or green through that visor, rather than the flat gray we see in photographs. Beyond invisible dangers lurked a physical threat, micrometeoroids striking at incredible speed. The moon gets struck by roughly 1,000 to 1,200 kilograms of space debris every single day, some traveling at up to 20 kilometers per second. At those velocities, even a speck of dust carries the destructive energy of a bullet, and with no atmosphere to burn debris up, anyone in the wrong spot was directly exposed. The suit's outer shell borrowed a layered, shielding technique from spacecraft hulls, designed to shatter projectiles on contact while cushioning layers underneath absorbed the remaining energy, keeping the pressurized inner layer intact. Protected by all this engineering, Armstrong and Aldrin made it through their first historic steps unharmed. But there was no time to celebrate. A demanding checklist lay ahead, with only about 2.5 hours to complete it. The first priority was collecting a lunar sample. Within minutes of stepping off the ladder, Armstrong scooped up loose surface material and tucked it into a pocket on his suit, so even an immediate abort would not leave the mission empty-handed. That decision mattered more than anyone realized, because the real scientific centerpiece was a suite of instruments the astronauts carried down and set up on the surface, weighing close to 50 kilograms. One standout device was a small array of precisely cut glass prisms, allowing scientists on Earth to bounce laser beams off the surface and measure the exact round-trip time of reflected light, letting researchers measure the Earth-Moon distance to within a few millimeters. Decades of measurements using that same reflector eventually revealed the moon is slowly drifting away from Earth at roughly 3.8 centimeters a year, and scientists are still bouncing lasers off that same hardware today, including recent work in 2026 by a laser-ranging observatory in China now using the aging reflector to study gravitational waves. The other major instrument left behind was a seismometer. This device, along with later ones, revealed the moon was far from the dead, silent rock many imagined, trembling instead with moonquakes from 4 distinct causes. Some originate hundreds of kilometers underground, triggered by Earth's gravity flexing the moon's interior. Others begin closer to the surface, caused by the crust shrinking as it slowly cools, sometimes lasting up to 10 minutes. 2 more happen right at the surface, one from meteorite impacts, the other from the intense heating and cooling cycle between lunar day and night, something future lunar bases will have to plan around. By the time the astronauts finished, they had collected roughly 21.5 kilograms of lunar material. Dark basaltic rock and fine dust that had sat undisturbed for billions of years, never touched by any living organism. Those samples became an extraordinary record of the solar system's early years, preserving chemical clues about the young Earth and the violent impacts that shaped our cosmic neighborhood. After 2 hours, 31 minutes, and 40 seconds on the surface, time was up. Aldrin and Armstrong climbed back up the ladder and sealed the hatch behind them. Even though their backpacks held roughly 4 hours of oxygen, mission planners had limited the excursion to 2.5 hours, keeping a safety margin in reserve. They left behind their tools, footprints, and a small American flag, carrying home physical evidence tied directly to the origins of our solar system. Yet the mission was still only half finished, and exhausted, coated in clingy, electrically charged lunar dust, the astronauts faced the riskiest part of the journey. Everything standing between them and a lonely death on the surface came down to one engine that had never actually been fired before. Not once. In the real conditions, it now had to survive. There was no backup, no way to repair it, no possibility of rescue. Making matters worse, Aldrin noticed the plastic switch controlling the circuit breaker for that critical ascent engine had snapped off, likely knocked loose by a bulky backpack brushing the control panel. Without that switch, the engine meant to lift them off, the moon might never ignite. With no replacement available, Aldrin improvised, wedging the tip of a felt tip pen into the tiny opening where the switch had been, using it to manually trigger the breaker, an almost absurdly simple fix for a problem that could have stranded 2 astronauts permanently on the moon, and it worked. Out on the moon, there are no do-overs. The lunar module carried roughly 73 hours of breathable air, nowhere close to enough to wait for a resupply mission from Earth. To make it home, the ascent stage had to precisely intercept the command module, racing through space at more than 5,000 kilometers an hour. Missing that window by even a few seconds could send the crew drifting into a useless orbit or falling back toward the surface with no way to stop. With no atmosphere for aerodynamic assistance, the crew depended entirely on precise computer guidance, which had to calculate exact engine burns while compensating for mass concentrations, hidden pockets of dense rock beneath the surface whose uneven gravity could quietly nudge a spacecraft off course. At just over 124 hours into the mission, the countdown reached 0, and thanks to Aldrin's pen repair, the ascent engine fired exactly as needed. The stage rose almost straight up for roughly 8 seconds before tilting into a steep climb, redirecting thrust to build the horizontal speed needed to reach orbit. Because lunar gravity is only about 1/6 as strong as Earth's, this climb was achievable using a single engine that could not even be throttled, but it demanded absolute precision throughout. After a continuous burn, the spacecraft settled into an elliptical orbit roughly 17 by 87 kilometers above the surface, exactly matching what mission planners had calculated. The lunar surface was finally behind them, but danger remained. About an hour after liftoff, the ascent stage fired thrusters in a carefully planned sequence to circularize its orbit and bring it parallel with the command module. From there, the hunt to close the distance began. Roughly 2.5 hours later, the crew carried out one final precise burn to set up a direct intercept course. And around 10 minutes after that, Armstrong finally caught his first glimpse of the command module. You might assume this maneuver would be simple for experienced test pilots, but in the vacuum of space, human eyesight becomes surprisingly unreliable. Without atmosphere to provide a sense of scale, depth perception essentially collapses, and distances become almost impossible to judge by eye alone. That is exactly why the bulk of the rendezvous was handled by an onboard guidance computer, with radar aboard the lunar module pinging out and a transponder aboard the command module pinging back, feeding positional data into the computer while the human crew monitored closely. Only in the final stretch, once both spacecraft were moving at nearly matched velocities, did the astronauts take manual control. Everything worked exactly as planned. The docking probe clicked cleanly into the receiving mechanism, triggering a set of capture latches, and as cabin pressure equalized, a full ring of additional latches engaged around the docking collar, creating an airtight seal. Aldrin and Armstrong were finally safe, reunited moments later with Michael Collins, who had spent the entire excursion completely alone in lunar orbit, quietly carrying the knowledge that if the ascent engine had failed, he would have had to return to Earth without his crewmates. There was no time for celebration yet. The crew transferred their precious cargo of samples between spacecraft, and before long, the empty ascent stage was released, left drifting alone in lunar orbit. All that remained was the 2.5-day, 384,000-kilometer trip home, far from a simple cruise. With every passing hour, Earth grew larger in their windows, but the crew noticed something strange that had been happening the entire time, something none of them could quite explain. Whenever they closed their eyes in the darkness of the cabin, they kept seeing brief flashes of light that clearly should not have been there. Buzz Aldrin later described them using words like spots, streaks, and even small supernovas, and the crew worried these odd flashes might signal exhaustion, or worse, a malfunction on board. As it turned out, a physicist had actually predicted this exact phenomenon back in 1952, decades before Apollo 11 flew, though his work had been largely overlooked. His theory suggested that once astronauts left Earth's protective magnetic field, high-energy particles from deep space would occasionally pass directly through an astronaut's eyeball. And as one moved through the fluid inside the eye faster than light typically travels within that fluid, it would create a tiny optical shockwave, producing a faint flash through a process called Cherenkov radiation. Though not fully confirmed until years after Apollo 11 flew, these first-hand reports helped kick off dedicated research into the phenomenon across the remaining Apollo missions, research that still matters today as agencies plan much longer missions to Mars, where astronauts would face these same particles for months rather than days. But even as the crew rested through these flickering lights, their spacecraft was steadily accelerating toward a genuinely dangerous encounter. Traveling at speeds beyond 39,000 kilometers an hour, Earth's atmosphere stops behaving like something soft and forgiving. Hit it at the wrong angle and the air might as well be a solid wall. Their safety came down to two things: the precise trajectory calculated ahead of time and the physical protection built into the spacecraft. The command module needed to hit a specific entry corridor, an angle close to 6.5 degrees relative to the horizon, and the margin for error was brutally tight. Come in too steep, beyond roughly 7.5 degrees, and the capsule would dive too fast, generating heat far beyond what its shield could handle and crushing the crew under extreme deceleration. Come in too shallow, under about 5 degrees, and the capsule would skip off the top of the atmosphere like a stone skimming water, bouncing back into an unstable orbit, and since the modules supplying their oxygen had already been jettisoned, the crew would be left drifting helplessly with no way to try again. Even on a perfectly calculated path, the descent was brutal, with white-hot temperatures reaching roughly 2,700 degrees alongside crushing gravitational forces, pushing the body close to its limits. Absorbing all of that required clever engineering built into the spacecraft's shape. Rather than sleek and streamlined, the command module was built as a wide, blunt cone, a deliberate choice discovered through hypersonic research in the 1950s. By refusing to be aerodynamic, the capsule prevented air from flowing smoothly around it, instead compressing that air into a detached shockwave sitting just ahead of the vehicle, a cushion of superheated compressed air redirecting the worst of the heat around the spacecraft rather than into the hull. Whatever heat did make contact was absorbed by a low-density ablative heat shield arranged into tiles, a fiberglass honeycomb structure filled with resin designed to chemically break down, char, and flake away, carrying enormous thermal energy off the spacecraft. For that process to work reliably, the shield had to be built with essentially zero defects, which was not something mass-produced on an assembly line. Resin had to be carefully injected into hundreds of thousands of individual honeycomb cells one at a time, and even a tiny air bubble risked a catastrophic burn-through. Technicians used tools resembling industrial caulking guns to fill every cell by hand, followed by X-ray inspection of the entire shield, a process that could take several months for a single capsule. The payoff was remarkable. While the outer shield glowed white-hot and disintegrated in a shower of sparks, the pressurized cabin and the 3 astronauts sitting just inches away remained at a comfortable room temperature the entire time. At least that was the plan, and now it had to actually work. The command module slammed into the atmosphere at close to 40,000 kilometers an hour, friction stripping electrons from the surrounding air and forming a glowing sheath of ionized gas around the capsule that completely blocked radio communication. Back at mission control, the consoles went silent, and that re-entry blackout lasted about 3 harrowing minutes, a stretch where the crew was sealed inside a cocoon of superheated plasma with no way to communicate, and no way for mission control to know whether they had survived. Inside, the view looked otherworldly, a chaotic swirl of orange and glowing green light as the heat shield burned away, while the crew was pressed hard into their seats under roughly 6.5 times normal gravity. Around 20 kilometers up, the fireball finally subsided, and radio contact crackled back. Shortly afterward, the protective cover was jettisoned, stabilizing parachutes deployed, and 3 large orange and white main parachutes unfurled, slowing the roughly 5,000-kilogram spacecraft to a survivable speed of around 35 kilometers an hour. Minutes later, the capsule struck the Pacific Ocean, landing safely. They had survived the fall, but nearly 2-meter-high ocean swells were not exactly a gentle welcome. Because the capsule's center of gravity was deliberately offset, it tended to settle upside down in the water, leaving the astronauts hanging uncomfortably from their seat straps. To prevent that, large inflatable bags built into the nose automatically triggered, flipping the spacecraft upright and stable. All that remained was waiting for a recovery ship, but the ordeal was not quite finished. Even as the hatch swung open, there was no immediate celebration because scientists worried lunar material might carry unknown biological hazards. The returning crew was met not by cheering family but by a biological containment team, and right there in the Pacific, Armstrong, Aldrin, and Collins were sealed into full-body isolation garments, transported by boat, and locked away inside a specially built quarantine facility in Houston. For their first 21 days back on Earth, the men who had just walked on another world spent their time behind thick glass, watching the planet celebrate their achievement from inside a sealed room. Armstrong even celebrated his birthday in quarantine, though the kitchen staff at least made sure he got a proper cake. Looking back now, decades later, our understanding of what the Apollo 11 crew actually brought home keeps getting deeper thanks to analytical tools that did not exist in 1969. Scientists re-examining these same samples have uncovered small but genuine traces of water locked inside the rock, something nobody expected from a world long assumed to be bone dry. It is a strange thought that dust scooped up in seconds during a rushed excursion is still teaching scientists new things about the moon, and about Earth, more than half a century later. Researchers now believe much of that water, along with other volatile chemicals like nitrogen, made the long journey from Earth itself carried off by the solar wind and guided across space by our planet's magnetic field over billions of years. According to detailed simulations published only recently, Earth's magnetic field does not simply block particles from escaping. It can funnel a steady trickle of charged atmospheric particles outward along invisible field lines, some reaching far enough to intersect the moon's orbit. Over enormous stretches of time, this slow transfer has left the lunar surface holding a chemical diary of Earth's own atmospheric history. Hidden inside grains of dust, the astronauts have scooped up almost without a second thought. Even the sample's magnetic properties hid an unexpected twist. For decades, researchers argued whether the moon ever had a genuinely strong magnetic field, since readings from different Apollo rocks kept contradicting each other. A recent reanalysis finally settled the disagreement, revealing the moon's ancient field was usually weak, just as one side had argued, but that it also experienced short, intense bursts where its strength briefly surged beyond even modern Earth's, exactly as the other side had claimed. Both groups had been right all along, each looking at a different slice of the same complicated history, since the Apollo landing sites happened to sample rocks, formed during some of those rare, powerful bursts. Other recent studies have also turned up microscopic traces of material apparently blasted onto the moon from distant asteroid impacts, and possibly from lunar volcanic activity more recent than scientists once assumed, raising fresh questions about how geologically quiet the moon really has been. Some researchers now argue the standard picture of a lunar surface gone completely dead billions of years ago may be too simple. We often remember only the names Armstrong, Aldrin, and Collins, but Apollo 11 was carried forward by the quiet, coordinated effort of hundreds of thousands of engineers and support staff, including a young engineer whose split-second decision to trust an overloaded computer and an astronaut whose quick thinking with a felt-tip pen may have made the difference between triumph and tragedy. Every kilometer traveled was built not just on rocket fuel, but on an invisible foundation of human expertise and split-second improvisation under nearly impossible pressure. Apollo 11 accelerated technological progress in ways that reached far beyond space travel, helping push forward the microelectronics that eventually became the backbone of modern computing. It turned what once seemed an impossible dream into a repeatable engineering process, one that still shapes how we plan complex missions today, and one whose lunar dust, scooped up in frantic seconds by two exhausted astronauts running dangerously low on fuel, is still surprising scientists more than 55 years later.